Okay, this lecture is about the study of the inverse of hyperbolic function. In the previous discussion, we have already defined what is the 6 hyperbolic functions. Each of these hyperbolic functions, some of them are 1, some of them are not. So if you restrict the domain of these hyperbolic functions to a domain such that the hyperbolic functions is 1, then you can define the inverse of that. So let us look at this hyperbolic function one by one. The one we want to see is the hyperbolic functions of sine. So the hyperbolic function of sine, it's I think given by the blue color line here. So this blue color line, which is written as x equals to hyperbolic sine y, is actually the reflections of the hyperbolic function of sine x. Now maybe I should correct what I said a minute ago. Here you have two graphs. The original function is y equals to sine function. So the yellow color function is the hyperbolic sine function. So when you make a reflections about the y equals to x-axis, then you obtain the blue color function. Okay, so the blue color functions is just expressed as the inverse of the hyperbolic sine function. So you can also label the blue color function y equals hyperbolic sine by another form, which is x equals to sine y. So so the blue color line is the inverse for the hyperbolic function. So from these very simple reflections about the y-axis, then you can realize what is the domain and range of the inverse hyperbolic sine function. So here it is obvious that the domain of the inverse of the hyperbolic sine function is inclusive of all values of real number, whereas the range is limited to what? I think it's limited to not quite. I think it is not limited. I think it is also a function that is ranging from negative infinity to positive infinity. So that is the range and domain of the inverse hyperbolic functions. So you don't really need to remember the shape of the inverse of the hyperbolic function. You can just remember the shape of the hyperbolic function of sine. So hyperbolic function of sine is an odd functions, and at x equals to 0, the hyperbolic sine function is 0. So the hyperbolic sine function would behave like this. Therefore, when you make the reflections about the y equals x-axis, then you would get the reverse or the inverse of the hyperbolic sine. So this is labeled as hyperbolic sine. Then when you make the reflections, let's see how you do that. I think the reflections, sometimes I'm not good at that, but you should be able to be visible, try to sketch out the reflections. I think it would be something like this. It is, I think, going to like this. Okay, so that would be a reflections from this line to this line, and this color line, the green color line, it will be just a reflection of this portion and get you the green color, right? So reflect this graph, you get this graph. So that would be the graph of hyperbolic sine. Okay, so that is what the graph, what it's trying to show, the green color, blue color line. Now, likewise, you can try to see if you can reconstruct the graph of the hyperbolic cos function and its inverse. So here, I would like to show you how I construct the hyperbolic cost function by referring to my mathematical code. So what I do here is first I plot my cost function. That is what I get. So this is the cost function that I have shown you in the previous slides. It's made up of the sum of e power x plus e power minus x and divided by 2. So we look at this hyperbolic cost function. The important thing that you have to note is that the hyperbolic cost function is not an one-one function. So by default, we choose to define the inverse of hyperbolic cost function by restricting the domain of cost to be only in the x value, which is positive or 0. Right? So you just limit x to be larger or equal to 0. Then you would have a hyperbolic cost function to become 1, 1. Then you reflect the hyperbolic cost function about the y equals to x-axis. Then you get the inverse of hyperbolic cost. This is what you get, right? So if you limit the x to be only positive, then you get these sections, which is denoted by this line, and this is the y equals to x-axis. So the reflection of the hyperbolic cost about the y equals to x give you this graph. So this graph would be then just the graph of the arc cost. So from this graph, it is quite straightforward to understand that the domain of range of the sine function, I think domain, let me type it here. Okay. So what I'm saying here is domain of arc cos of x is a value of x where x starting from 1 up to infinity, right? Up to infinity, not included, whereas the range of the arc cost from the graph of this red color, you can see that it's beginning from 0 and it goes to infinity all the way up. So it starts from 0 and it goes to positive infinity. So that is how you can remember the graph of the inverse of the hyperbolic cost function. Namely, this inverse is called the arc hyperbolic cost. So I call this as arc hyperbolic cost functions. Here is the symbol that represents the arc hyperbolic cost. So let me see. Okay, here this is a graph that I just shown you, which is the graph in the Mathematica, which is the red color. So if you compare it, you see that this graph is just the same as this blue color graph. The graph of y equals to inverse hyperbolic cost. Sometimes I call this arc hyperbolic cost function. Arc hyperbolic cost function. Okay. Then after you have constructed the inverse of the hyperbolic sine, the inverse of the hyperbolic cos, then let's see how you construct the hyperbolic tangent and its inverse. So first of all, you recall how your hyperbolic tangent function looks like. So this is the hyperbolic function for hyperbolic tangent function, TANH. So it is obtained by taking the ratio of the sine function, hyperbolic sine, divided by the hyperbolic cos. Right? So this is the green color is hyperbolic sine divided by the hyperbolic cos, which is a blue color line. So this is the shape of the hyperbolic tangent. So the hyperbolic tangent, as I mentioned here, its range is limited to between -1 and 1, but 1 or -1 at the endpoint are not included. So this is the range of the hyperbolic tangent. So in order to obtain the inverse of the hyperbolic tangent, what you need to do is to choose the domain such that the hyperbolic tangent is 1, 1. And it's obvious that the hyperbolic tangent function is all the while 1 to 1 for all the domain of x. So you don't need to restrict the domain of the hyperbolic tangent 1. The functions of hyperbolic tangent is naturally 1, 1. So you just need to plot a y equals x-axis, y equals x line, then you reflect the tangent function, hyperbolic tangent function about the y equals x, then you get this red color line. Right? So the red color line appears to be then the inverse of the hyperbolic tangent function. So here again, I just write down the domain of hyperbolic tangent function of x is just equals to minus infinity to positive infinity, which is just basically the real number, and then the range of hyperbolic tangent is just going from -1 to 1, but not included. Now, if you have already obtained the range and domain of the hyperbolic function, then the inverse of it, the inverse of the inverse of the hyperbolic tangent, which is the arctangent, then has the domain, which is the same as the domain of the original hyperbolic tangent function. Right? So the range and domain of the function and the inverse of it change. So the range of the inverse hyperbolic tangent is just equals to the domain of the tangent function, which is from negative infinity to positive infinity. So you look at the red color line, right? The range is going from negative infinity up to positive infinity, but its domain is only limited to be between -1 and 1. And the endpoint of 1, 1 is not included. So let's continue to look at the functions of hyperbolic secant. So this is the function of hyperbolic secant, which I already discussed in the previous lecture. So you look at this one, it is obvious that the hyperbolic secant is not 1, 1. Therefore, you have to limit the domain of hyperbolic secant to be only taking the 0 or positive side on the real axis. So you have to limit the hyperbolic secant to only positive side. That is what you get. Right? So this is the positive side of the hyperbolic secant, which is just equals to this one. Right? So in order to obtain the inverse of the hyperbolic secant, then you just reflect the hyperbolic secant about the y equals x-axis to obtain the red color axis, the red color curve. And this red color curve is just the arc of secant function. So from here, again, you can obtain the quite straightforwardly the domain and range of the functions. I think there's something wrong with this. Never mind. So let me write it down here. The domain of hyperbolic secant x is just equals to the values of x up to infinity, and start from 0 up to positive infinity. That is the domain of the hyperbolic secant. Then the range of it, can see it from the graph, is going from 0 to 1, but 0 is not included, right? So the range of hyperbolic secant is starting from 0, but 0 is not included, and then it would end up to 1, and 1 is included. Right? So this is referring to the range of hyperbolic secant starting from x or y equals to 0, but 0 is not included, and all the way up to maximally 1. Right? The hyperbolic secant, the hyperbolic secant will never has a value which is negative or larger than 1. Maximum it can go is just 1. And once you have obtained that, then can easily answer the question of domain of arcsecant and the range of arcsecant. So the domain of arcsecant is just a range of secant. This, and then the domain of arcsecant is just the range. So the range of arcsecant is just the domain of secant, right? So this is the red color arcsecant function. So arcsecant function defined or for a domain from 0 to 1, but not inclusive of 0, and the range start from 0 up to positive infinity. So that is the range of arc sine. So you can do the same thing for cosecant and arccosecant. So there it is, the arccosecant, sorry, for cosecant function, hyperbolic cosecant function, which is sometimes written as CSSH in Mathematica. So this is the hyperbolic cosecant function. Hyperbolic cosecant function is just 1 over hyperbolic sine, right? So the green color is hyperbolic sine. So if you take the reciprocal of it, then you get two graphs which are all 1, 1, right? So this is the graph of hyperbolic cosecant, or when x is positive, and this is the graph of hyperbolic cosecant when x is negative. And you do not need to restrict the domain of the hyperbolic cosecant because it's already a function which is 1, 1. So from here, the domain of hyperbolic cosecant is from minus infinity to positive infinity. So in order to obtain the inverse of the hyperbolic cosecant, just reflect the hyperbolic cosecant functions about a y equals x-axis. Again, the black color line is the original hyperbolic cosecant. When you reflect it on this y equals x-axis, then you get this red color. Okay, so this red color is obtained from reflecting the black color line about the y equals x-axis. So this is the shape of the hyperbolic shape of the inverse of the hyperbolic cosecant. So I'm going to write it down. Domain of cosecant, hyperbolic cosecant function is real part, right? It's just the real functions. It's just a real value that is defined for all x except 0. Okay, so this is the same as saying it is just equals to, well, from minus infinity to 0 and union 0 to positive infinity. So this is another way of specifying or describing the domain of the cosecant function, which does not include x equals to 0. Then from here, you can also easily see the range of cosecant functions is from minus infinity to positive infinity, except x equals to 0. So the range and domain of the hyperbolic cosecant are both the same. So likewise, then you can easily come to the conclusion that the domain of arccosecant and the domain of and the range of arccosecant are also the same. Right? So the red color line is the arccosecant, is also the arccosecant on the left hand side. So the range and domain of this red color graph is obviously described by this and this for its domain and range. So that is for the arccosecant, and for the cotangent functions, it looks like this. So this is the cotangent function, right? The hyperbolic tangent function is like this. So the reciprocal of it gives you the hyperbolic cotangent. So the hyperbolic cotangent function will behave like this. And again, hyperbolic cotangent function is an 1, 1 function. Therefore, you don't need to limit the range, the domains of the hyperbolic cotangent functions. So it will still be 1, 1. And here, the range and domain of the hyperbolic cosecant function is still the same. So let me write it down. I think it's exactly the same as that for for the previous case, the case for the hyperbolic cosecant. Okay, so the range of cosecant domain range of cotangent hyperbolic cotangent function is this, right? So the blue color, the black color line has a domain from minus infinity to positive infinity, exclusive x equals to 0, and from minus infinity to positive infinity for the range without 0. So that is the range and domains of a hyperbolic cotangent. Then you can again reflect the hyperbolic cotangent about the y-axis to obtain the red color curve. Right? The red color curve, like here, is obtained by reflecting this black color curve about y equals x-axis. Now, it doesn't look very nice because the graph that's shown here is not really what we call to scale, right? So the x scale and y scale are not equal to each other. The scale along the y is like longer than the scale along the x-axis or vice versa. But they should be symmetrical to each other when you make the scale of the x and y axis to be the same. It's just that here it's not shown to be the same because the aspect ratio is not set properly. Okay, but anyway, the red color line is still the reflections of the black color line about the y equals x-axis. So again, the range and domain of the inverse function, that is the domain of arc cotangent and the domain of arc cotangent and the range of cotangent are also the same, right? So it looks like for these 6 hyperbolic functions and its inverse, in order to obtain the inverse, you have to, in some cases, restrict the domain of the hyperbolic function. Out of these 6 different functions, only the hyperbolic cos function, you have to impose the restrictions to take only x equals to positive. Whereas for the other hyperbolic function, such as hyperbolic tangent, hyperbolic sine, this one, hyperbolic cosecant, and the hyperbolic cotangent, out of 6 functions, 4 do not need to restrict the domain, but you need to restrict the domain of the hyperbolic secant function to only positive in order to obtain an one-one function to define the inverse for hyperbolic secant. And so is for the hyperbolic cos. The hyperbolic cosecant functions has to be restricted to only positive x in order to obtain the hyperbolic cotangent function. Okay, so this is just a detailed descriptions of these 6 different hyperbolic functions and its inverse. So at this stage, you should have a good idea of how the inverse of this hyperbolic function looks like, how they could be derived, and how they can determine the range and domain of this inverse function. What is shown in the screen here are the shape of the 6 different hyperbolic inverse of hyperbolic functions. This is the one, 6 of them, and also the other 3, which is shown here. Right? So this has been shown in the Mathematica code previously, so I'm not going to repeat it here. Now, after we have defined the inverse of the hyperbolic function, then there is a identity for these hyperbolic functions. So remember also for the hyperbolic functions, for the hyperbolic function also, they have its own identity. The inverse of the hyperbolic function also have a set of identity, which is kind of like straightforward and simple. That is the inverse hyperbolic secant function is just equals to the inverse cosecant inverse of hyperbolic cosecant function with 1 over x, and you have this very simple looking identity which could be just understood quite easily. Now, how can you understand that? It's just very simple. Let's try to see if we can prove this. Now, of course, I can just show you the slide and then give you the answer, but I would like to work it out so that you have a stronger memory of what is happening and how to prove these statements.